Hello everyone and welcome to this WEkEO training on coastal interactions. I'm Alexandre Brun from Noveltis and I will be presenting you this Jupyter notebook. So today's subject will be storm surges and it will be applied on the case of Hurricane Helene, which happened in September 2024. So storm surges usually refer to high winds and low atmospheric pressure that cause big floodings in coastal areas. So this leads, of course, to significant inundations of, sometimes inhabited, sometimes not areas, causing damage to infrastructure, to houses, and also a threat to human lives and living ecosystems. And so to illustrate this, we're going to study the Hurricane Helene, which here struck the coast of Florida in last September. So this event was a stark reminder of the destructive potential of these events. And it of course shows also that it is crucial to use techniques to monitor such events. So you will see that we'll be using remote sensing data and in-situ data. So for remote sensing, satellites with altimeters or scatterometers are of great use to track these hurricanes, and that's what we're going to see in this training. So first, we'll be using the Python programming language. So the recurrent modules are described here. We'll be using NumPy, which is very commonly used for scientific computing. Xarray is also very common for computing scientific data and reading files that are in netcdf or HDF5 formats, for instance. Matplotlib and Cartopy will be used to draw figures and maps. GeoPandas is a library that allows us to work with geospatial data. And finally, Rasterio is a powerful tool to process and plot 2D scientific raster data, for example, satellite images. So on this cell, I'm just going to import everything. If you're using the WEkEO Jupyter Hub, you can just use the WEkEO Lab kernel. Make sure that you have this activated because it will have all those libraries pre-installed and available. So here's a brief section about the data access and about the product that we're going to use at the beginning of this training. So the product we're going to use is a combination of model and satellite observations, which is called Global Ocean Hourly Sea Surface Wind and Stress from Scatterometer and Model. So if you want to know more about the product, you can click on the link to open the dedicated WEkEO page. So as you can see here, you have all the information you need about the product, how it is calculated, and you can even go to the official page to have access to the user manual and so on. And you can open it and on the WEkEO viewer and have access to the different variables that are available. I don't know, I'm just going to open, for instance, atmosphere vorticity bias, and there you go. And so to download it for Python, so here are a few more information about the product. So this is hourly data, this is a spatial resolution, and this is the temporal coverage of the data. In our case, we'll be only using data for September 2024 because this is the time frame where the hurricane happened. So to retrieve the data, you have a few resources here on those links to have tutorials to if you want to have an article about how to download data. So here are a few cells to set up your .hdrc file. So basically, if this file is necessary to have access to the WEkEO API and to download data. So if you don't already have one, execute this cell because it will ask you for your credentials, so username and password, and create this file in your home directory on the Jupyter Hub. And once you have it, you're good to go to download data. So now to actually retrieve data. So here is an example here of a data request that I have written for this training. So I can show it to you. So it's my data folder at ATM for atmosphere, and this is the request that I've made. So you can see that this is the ID of the dataset, the time frame that I want. So I see I'm only selected September. The bounding box of my area of interest, which is centered around Florida. And those are the variables I want, so eastward wind and northward wind. And so if you want to write a similar request, it is very simple. So you can just go to the WEkEO data viewer. And here is the dataset that I've opened, and when I click on download, I have a few options that are displayed. So for instance, I can see here set up a bounding box, etc. I'm going to go very quickly on this. Choose a variable, start date, etc. And now if I show API requests, I have my request that I can just copy and paste in the Jupyter Hub. So this is what I've done. I've just shown it to you. Here I'm just printing it in the notebook. And now I'm not going to execute this cell because my data is already available here. But using this cell, you will be able to search the data using the API. And if you uncomment this line of code, you can download the data that your request has found. So now that we have downloaded the data, let's open it and see what's inside it. So we've just opened our file, which is here, and you can see that it has a very long name, but it's not a problem. And so this is what we have. So we have 1 month of data. You can see that it goes from September 2024, from the 20th to October, to the 1st of October 2024. You can see that I have the two variables that I've just asked for in my request. And if you click on those icons, you can know more about those variables. So here is the wind speed on the eastward component, and here on the northward component. You can see that it is in meters per second. And here, a longer name, you can see that the wind is measured at 10 meters above the surface. So our dataset seems valid. There doesn't seem to be any pre-processing to do. So I'm just going to show you a few basic data manipulations to perform when you want to use a dataset with Python. So basically, we're going here to do a few examples using the time coordinate or dimension. So here I can just display the time variable when typing it like this between brackets. And now what I want to do with the dataset, we often want to select a shorter date range when processing the data. So here is an example of just choosing one date in the dataset. So if I know the exact date here, for example, the 27th of September at 11 AM, I can select it like this using the cell function. And you can see that now the time coordinate has this dimension and disappeared because I've only selected one. So now my dataset has only two dimensions, latitude and longitude. And if you don't know the exact date that you want in the dataset, you can select any date and use the nearest method, and we select you the nearest data point in your dataset. So, for instance, I've selected a date that was too precise here with 4 p.m. and 35 minutes, and here it selected me 5 a.m. So 4 a.m. 35, and this is 5 a.m., which was the closest date. And if you want to select, for example, using an index philosophy to select data, you can use the iCell function and select here. I'm selecting the fourth date, if you count from 0 of the dataset. And finally, if we want to select several dates, you can use the slice method. It will allow you to select all the dates between a starting date and an ending date. So now you know how to subset a dataset. We'll try to visualize our data. So what we want to do first, we will want to, in this section, just draw a map of the wind speed over Florida. So we have the northward and eastward components. What we want to do is to compute the total wind speed. So we're just going to calculate it using, the Pythagorean theorem. Which will be the square root, the total wind speed is equal to the square root of the vertical and horizontal components, which is what we are doing here. So this is a way to set up a new variable in the dataset that is now available here. And now that we have this variable, we can use it to draw the map of the wind speed. And we'll still be using the eastward and northward component because we want to know also the direction of the wind on our map. And so we'll be using those two components to draw a vector field of the data. And this is what we are doing here. So to draw the map, we are simply going to use the pcolor method from Matplotlib. And to draw the vector field, so the arrows on the map to show the wind direction, we're going to use the quiver function. So before using quiver function, you need to set up a little bit the data grid. So I'm doing this here. I'm coarsening the dataset a little bit to have big pixels because there is one arrow per pixel, and if you don't coarsen the dataset to have big pixels, we won't see anything. We need to compute the grid using saving the latitude and longitudes on variables. And once this is done, we can pass all that into arguments for the quiver function. And for the pcolor, it's much simpler. We just have to, as arguments, to select longitude and latitude, and say that we want the map colored as a function of the wind speed. And here we're just selecting the color map that is called the magma. You will see what it looks like just below. And here are a few lines to write the titles, name the axis, name the color bar, etc. So this is our hurricane. We can clearly see it here with the arrows circling around this circle of high wind speed. We can see that this was taken on the 25th of September 2024 around 9 p.m. So now to monitor the hurricane, we'll be working around this date to see exactly what was the trajectory of the hurricane. So moving on. So to monitor the trajectory of the hurricane, we're basically going to plot several graphs like this one. At all the successive dates that we have, and we'll then compute an animation in order to have an animated image. So we're going to plot this to monitor the trajectory over from the 25th to the 27th of September 2024. And this will allow us to to compute this graph for all those dates. So this is what I'm doing right now. I'm plotting here exactly the same graph at several dates here. So this is why it's taking more time to execute, because I'm plotting several dozens of images. So we'll just wait a while before it's finished. You can see here that I'm saving all my images. Here we're using the save thing function in another directory. I'm going to show it to you. It is here. So you can see that I have a lot of images that have been plotted here a few seconds ago. But now apparently it's finished executing, so we can move on to plot the actual animated image. So we'll be using those functions just for this, those libraries, sorry. So here I'm setting up my GIF image with the duration of each frame. So here we'll be having 100 milliseconds per image in the animation. And now I can display it, and you will see the trajectory of the hurricane with the evolution regarding the dates. So of course you can see that contrary to the previous plot, I haven't plotted the arrows of the vector field, because of course it will be a lot less easy to read. So now that we have monitored the trajectory of the hurricane, we will try to see how the magnitude of the storm surges that it caused near the coasts. And to do this, we'll be using in situ data. So we'll be actually using measurements from local tide gauges that are set up and available all around the coast of Florida. So those are available on the website of the American National Oceanic Service. So here on this map you can see that we have several tide gauges that are available, and we can select each of them and retrieve data from them. So this is what we're going to do here, and show you well, what's inside those measurements. So all of those measurements are already pre-available in for this training. So just go to this to the TG folder for tide gauge, and we've prepared a few tide gauges, but you can, as you can see, you can download more if you want. So if I open one of them, so it's one of those files, it corresponds to the tide gauge that is located in Cedar Key in Florida. So if we go to the map, if I remember well, it's around here. Yep, this is this one. So this is the tide gauge that we're examining right now. So if I open it, I can see that I have the sea level here as measured as an anomaly with regards to the mean sea level. I have a predicted sea level and a verified sea level. So we can see how those two quantities correlate. And here I have the date and a time column. Well, to have the time series for the measurements. So first of all, this format of one column with the date and one column with the time is well, not suitable for Python processing. So we're going to do a bit of processing to have a single column having the full datetime information in a format that is recognizable by Python. So this is what we do in this cell. So basically we just combine the two variables using the aggregation function. And when we do this, you can see that we have a single datetime function, datetime column, sorry, which is in a different format that is interpretable by Python. So now we will be able to plot the data. So let's do that here. So as you can see, we will be plotting the predicted quantity sea level versus the verified sea level over the period that we have selected. So from 20th of September to the 4th of October. So this is the location of our variable, and you can see here that the predicted sea level was quite a regular quantity. However, the verified one, so the observation, goes much higher near the during the 27th of September, which is the time where the hurricane struck the coast of Florida. So here the storm surge is clearly visible. So now for the next cell, we're just going to do the same operation to plot the verified sea level for other tide gauges that are located in the area. So here you can see that we have selected a few more of them. And of course you can reproduce this operation on others that you may find here on this website. So you can see that for each of them, I repeat the operation of reprocessing the date time. And now I plot all of them, only the verified quantity here, and see what we have. So executing the cell, you will see that here are all the locations of my tide gauges. Here are the corresponding names with the associated colors, and here are the sea levels. And for each of them, we can see that we have a strong storm surge here. Still, the strongest still being Cedar that seem to have been hit the hardest by the hurricane. But we can see, for example, here for Clearwater Beach, which is quite close to Cedar Key, we do have also quite a strong storm surge. So we can see that Cedar Key is one of the places that was hit the hardest by the hurricane, and now it's highly probable that the area or neighboring areas have been flooded by this storm surge. So we're going to examine this now using satellite images. So to look at the coastal impacts of the hurricane, we're going to use Sentinel-2 images. So we're using Sentinel-2 images first of all because they have a high revisit rate, because we have one new image every 5 days. So for monitoring exceptional events like this, it is quite convenient compared to other available satellite imagers. It has a spatial resolution of 10 meters, at least for the spectral bands that we'll be using. We'll be using those spectral bands, which are numbered here but correspond to blue, green, red, and near infrared. So we have a medium-high resolution and quite high revisit rate, so which is perfectly suitable to monitor environmental phenomena like this. And of course, if you want to know more, you can either go to the WEkEO dedicated topic here for Sentinel-2, or go to the Sentinel Online web page, which has all the information you may need about the satellite. Okay, so here, just like with the wind product, I have written 2 requests for 2 Sentinel-2 images. So basically we're going to compare one image from September 22nd, which was before the hurricane, and one image from October 1st, which was soon after the hurricane. I have here written a request for those 2 images, so you're using their identifier. So same thing as before, I'm not going to execute this cell, but this is what should be used to download the data if it is not already available. But in my case, I've already pre-downloaded the data in the S2 folder here. So everything's ready. And once again, if you download the data on your own, it will be downloaded as a zip file, and you will need to unzip it. And to do this, you just have to execute this cell, but if you have already the files available, this is not necessary. So here is just to show you the location of our image. So it is very close to Cedar Key. It's a small city in this area, which is called Horseshoe Beach. If you want to, we can have a quick look on Google Maps. But of course, we will see it very closely using the Sentinel-2 images. Okay, so moving on. So this cell is used to define the area of interest around Horseshoe Beach, so delimiting the bounding box. And we'll be using this to trim the Sentinel-2 images only to this area of interest, because Sentinel-2 images are are squares with a side long of 100 kilometers. So we don't need to process that much data, which is why we're going to trim the data. Here is a reminder of the spectral bands that we are using. So as I told you, we are using blue, green, red, and near infrared. And here are the numbers. But of course, Sentinel-2 has many other available bands in this field, but they don't have a 10 meters of resolution. They are either 20 meters or 60 meters, which is which is coarser. So using this cell, we will open all the images. So you can see that we have each band is in a file individually. So we have to open all of them for the two images. So this takes also some time, but not more than a few seconds, I think. Okay, it's finished. So now all the images are opened, and first we can just plot in real colors the area that we are studying to see what it looks like before and after the hurricane. So as you can see here, we are lucky because this area is not too clouded, because clouds can be a problem when using satellite imagery, of course. So this is just an overview, but we can already notice a few differences. For instance, here this small estuary is much bigger after a storm. So this, for instance, is a sign of potential inundation. But we'll be monitoring this in more details because we will be plotting here, or computing here, the normalized difference water index. Sorry, I just found out that there is a small typo in the text. Okay, which is a great indicator, which is very commonly used also, to detect water in satellite images. So it consists in performing the normalized difference between the near infrared spectral band with the green band. So we will be using this and computing the water index for the September image and the October image using this cell, and plotting them to see the two water indicators. We can see that after the storm, the blue areas seem first of all bigger and in a deeper blue. And now we're going to compute using these water masks just by thresholding the two NDWI images. So this threshold is quite arbitrary. You can adjust it if you want, but this is what I've chosen to use. And here I've just computed 2 water masks, and if I subtract them, we can highlight on the areas that were not flooded before the storm and that have been flooded after. And so this is a result. So you can see here, for instance, that around the history that I've just shown you before, we have some blue here that accounts for the flooded areas that we had just noticed. Also, this area has been severely flooded, and we have this little shore here and this little shore here. We have to be careful because this patch here, for example, is left because of a cloud. If we remember, yes, this corresponds to the presence of a cloud, and the same thing goes for here. But here, for the other areas, we clearly have those areas have been clearly submerged with water, and you can see some spots here in the city, which may account for some damage that have been done by this hurricane. So as you can see, this shows very well that it is crucial to be able to predict, monitor, and assess the impacts of such events, because first we need to communities need to prepare in case such an event happens. It is also necessary to mitigate those events. So we've just seen a few techniques to use data for monitoring such events and their impacts. So we're reaching the end of this training. Here are a few exercises if you want to deepen the analysis. Here are a few easy exercises for beginners, like plotting the first map we did with the vector fields of the wind at other dates. Select other tide gauges to plot and look at the storm surge. And of course, we've chosen one hurricane as an example for this case study, but you can reproduce this analysis for other hurricanes if you're interested in this. Here is an example of a database of recent similar events, which you can take inspiration from, but it's really up to you. And if you're still interested in this hurricane but want to observe other areas that may have been affected by coastal floodings, you can reproduce this analysis on other areas of the Sentinel-2 images that we have downloaded. Or you can also download other Sentinel-2 images. Of course, make sure that you don't have that your area is not covered with clouds, and it will train you to use water indicator and or other indicators computation. Alright, so I think that we are done for this training. I hope you learned a few new things and that you enjoyed this training, and thank you very much for your attention. Goodbye.